Focus 11 is all about molecular spectroscopy, ways of looking inside molecules. And there are common features of spectroscopy. I mean, one common feature being that you need a spectrometer. Another common feature is that the intensities of transitions depend upon a quantity called the transition dipole. And the transition dipole, you should have clearly in your mind what it is, though it's got a quantum mechanical expression which involves a dipole moment operator, the initial wave function, the final wave function for the transition. It really is measuring how dipolar the electron migration is when a transition takes place. That's all. So if the electron moves spherically symmetrically in the transition, it's got no transition dipole. So it's not going to be visible in the spectrum. If the electron shifts from here to here, then it's got a transition dipole. And so it will have, is likely to have at least, some absorption characteristics. And the important thing is, in discussing molecular spectroscopy, really it's based on the concepts of stimulated absorption, where the electromagnetic field simply bathes the molecule and shakes it into undergoing a transition from initial state to a final state. Or stimulated emission, where once again the oscillating electromagnetic field around it shakes it and forces it to drop down into a lower state. Or thirdly, as Einstein identified, the process of spontaneous emission, where it simply spontaneously, without any photons of the same frequency around it, drops down and undergoes a transition. I mean, some people get puzzled by that because people think that everything ought to be caused. So is this an example of a transition that is not caused? No, it really is caused, because if you think of the electromagnetic field as a collection of harmonic oscillators, so you've got one particular frequency, then excitation of that oscillator corresponds to having one photon present. Excite it another time, you might have two photons present, and so on. If you haven't got any photons present, you've still got the 0-point energy of the harmonic oscillator. So the electromagnetic fields of the vacuum are still fluctuating because they've got 0-point fluctuations, even though you haven't got any photons present. And it's those 0-point fluctuations that cause the so-called spontaneous transition from an upper state down to a lower state. Everything is caused. Okay. And so they might be caused by invisible forces. So you've got these ideas of emission and absorption, and indeed of scattering, which gives you an entree into the world of Raman spectroscopy. I think the other major thread that one needs to know is how to measure the intensities in terms of the absorption of the radiation as it passes through a sample of a given length. And this introduces you to the so-called Beer-Lambert law, where the intensity falls off exponentially with distance through a uniform medium. And that means that you can parameterize the absorption intensity with various quantities like the molar absorption coefficient and so on. So you've got a number of numbers that can come. You've got a number of techniques that you can apply. And you've got a number of inferences, therefore, that you can draw. So the focus then works its way through the variety of spectroscopies, working its way upwards in energy, effectively. So there are rotation. First of all, we talk about the rotation of molecules. the rotation of diatomic molecules, which is quite easy to understand, but then the more complicated motion of polyatomic molecules and the quantum numbers that you need to describe their angular momenta, and through those angular momenta their various energies. And clearly a cigar-shaped molecule can rotate not only about its axis but are perpendicular to its axis as well. So you need to take into account the quantization of both kinds of motion. And although you could solve the Schrödinger equation for the motion of these molecules, it's much easier to take a shortcut, which is to say, look, we know the classical expressions for the energies. They're just in terms of the square of the angular momentum divided by the moment of inertia. So why not use those, but just replace the angular momentum by the quantum mechanical expression for angular momentum? So j into j plus 1 times h cross squared, things like that. So you can construct the energies of rotating molecules, rotating rigid molecules, very simply by invoking what you know already from quantum mechanics and sticking it on to what you should know from classical mechanics. And then you apply the concepts of the population of the rotational energy levels and the magnitude of the transition dipole moment between the various rotational levels to work out what the spectrum should look like. Then you move up a notch in energy and you talk about vibrations. And the key to understanding vibrations is really to realize that they can be expressed in terms of a harmonic oscillator. But when you've got a polyatomic molecule, you've got many modes of vibration. But provided they all behave like a harmonic oscillator, you can separate them all. And so you get what are so-called normal modes. It might be a breathing mode of methane, or it might be an antisymmetric stretch of carbon dioxide, something like that. And treat each one individually as a separate harmonic oscillator. And therefore just invoke what you already know from your study of vibrational motion to talk about their energy levels. And what you know about transition dipoles to identify the transitions that can take place. But then you realize that if you're in a gas and a vibration takes place, moments of inertia change. And so just like a skater on ice, if you bring in your arms, you go faster. There's a coupling between vibrations and rotations. And so in the gas phase, a vibrational transition of a molecule is accompanied by rotational transitions. So you have to look at vibration-rotation transitions and try to identify how to cope with them both simultaneously. And then thirdly, you get to electronic transitions. And the unifying principle here is a little bit like the Born-Oppenheimer approximation, but it goes beyond it. It says the nuclei are so heavy that when an electronic transition takes place, the nuclei are still asleep. They don't move. Of course, once it's taken place, they wake up and start to vibrate in the new in the new potential field. But the transition itself is simplified by the so-called, according to the Frank-Condon principle, by supposing that the nuclei are so heavy that electronic transitions are decoupled from them until they have actually finally taken place. So you don't have to think of the whole thing changing. Think of a molecule, think of it changing, and that gives you your electronic transition. Accompanied, of course, by the stimulation of vibrations, because by the time it wakes up in its upper electronic state, the nuclei are in a different force field, and so must start to vibrate. And if it's in a gas, then they can also rotate as well. So it gets rather complicated in that case. But it's simplified, as always, in these matters by introducing concepts like chromophores, which are little groups of molecules with characteristic absorption frequencies and so on. So one can talk about electronic transitions in a fairly straightforward manner. And finally, in this focus, there's the question of falling back down again. How does the energy of an excited state return, get discarded into the surroundings? And this leads you into concepts of non-radiative decay, when the molecule simply gives up its energy to the immediate surroundings, which are typically in a liquid, are jostling around it and ready to take up that energy, or under certain circumstances to introduce the concepts of fluorescence and phosphorescence, which are both radiative decay processes. And in fluorescence, really the molecule simply dribbles down into its lowest vibrational state and then drops down, emitting a photon to its original ground state. And in phosphorescence, there's the process of intersystem crossing, when the electrons decouple and switch from being, say, in a singlet state to being in a triplet state. So instead of being anti-parallel, they become parallel because of spin-orbit coupling. And then they can't do anything. But they can, if they wait long enough. They can slowly dribble back into the ground state, because the spin-orbit coupling breaks the usual selection rule. And so you get long-lasting photoemission, which is phosphorescence. So in this quick survey of what this rather long focus, I've taken you from the common features of molecular spectroscopy, which are common to all of them, through systems of increasing energy and therefore of increasing complexity of the spectra, from rotation through vibration to electronic, with each flea having a little flea on its back and so on. And then left you with the mechanisms by which you get back to where you started, namely fluorescence, phosphorescence, or non-radiative decay.